started to hear cracking because there was incorrect post tension on there. So they went and tried to tension it more, and it collapsed. And what happened in the picture that I saw, the post tension cable shot out of the concrete, and that only happens if it breaks, right? Like it breaks and it comes shooting out of the concrete. Like that doesn't happen by it just collapsing. So anyways, it's like a bullet coming out. What's my point? Engineers have to trust the math, right? And they can't do any slight variation to one thing and think that the math is going to be the same. Everything has to be accounted for. So trust the math. All right, let's move to the next question. Now, if I took those little symbols off this integral and put that problem on a test, would you just be so happy? Yes. I hope so. When you look at that, you should just be like, that's the easiest integral I've seen ever. If you're not at that point yet, then that's danger zone area right now for you. All right, how are we going to do this? Split it into two because you're going from negative infinity to infinity. Now, just in case you don't know what this graph looks like, and I don't know why you would, we've never talked about it, let's just graph it. If we plug 0 in for x, what do we get? We plug in 0 for x. We get 1. So that point's on our graph. And then think about this. If I start plugging in numbers here, right, for x, this is going to get bigger, which means this gets smaller, right? And so it's going to start diving down to the right. It actually does something like this, though. It goes like this, okay? And it goes forever. But this is an even function, so it's the same thing on the other side. So it looks a lot like a bell curve almost. And we want to know the area underneath this whole thing. All this area in here. It can't possibly converge, can it? I mean, that's a whole lot of area. All right, so first thing, we break it up into two integrals. We're going to go the integral from negative infinity, and then we get to choose where to break it. And we can pick any number we want in between negative infinity and infinity. 1 would be fine. I like 0, though. Do you like 0? I like 0. I'll do 1, but 0 seems to be right in the middle, and it's a nice number. And you could pick, if you wanted to, you could pick 3, right? You could pick E. You could pick negative 1/4. It doesn't matter. But I'm going to go with 0. All right. And then here's this. Plus, now I need to pick up from where I left off, which is 0, and now I go to infinity, and it's the same thing I'm integrating. So now I have two different improper integrals, and for each one of those I need a limit now. Limit now, right? What the hell happened there? Okay, so I go limit, t goes where? T goes to, I'm replacing this one, right? So negative infinity. And then integral t to 0 of 1 over 1 plus x squared dx. Then I'm going to add to that plus a new limit, right? Now I could use t again if I wanted to, but because I don't want to confuse the t's, I'm going to use a different letter. I'm going to use r, and that, I don't know why, because my name's Robert, so I'll use r, whatever. I don't have a good reason for it. R goes to infinity, integral, and now I'm leaving this to be 0, and this is going to be my r, right? Does this make sense? All I'm doing is the same thing we just did, but I've got two integrals now instead of one. All right. Next step. Yep. So I would do what? Antiderivative, right? We need the antiderivative now. So what is the antiderivative of 1 over 1 plus x squared? Arctan. Okay, arctan. Arctan. So this is limit t goes to negative infinity, then in brackets, arctangent of x, right? And then the evaluation bar t and 0. So I found the antiderivative of this, that's that, and then here's my limits of integration, so I put them in the bar, and I still have a limit out front. Then plus, still have another limit. Don't be afraid of the limit. Go ahead and write the limit down. It's your friend. Arctangent of x again, and then evaluation bar, 0 on the bottom, r on top. There we go. Questions? Next step, rewrite the limit again. T goes to negative infinity. Now, for this first limit, I've got two things I need to put in here, right, and subtract. And then for the next limit, I also have two things I need to put in here and subtract. All right, so this one right here, 0 first, right? Arctangent of 0. And then the other one is arctangent of t. And then on this one, it's arctangent of r, and then arctangent of 0. You with me? Some of these I actually think I know, like the arctangent of 0. It's 0. Why? How? What? How'd you get that? Because what? Are you cheating? Do you have like a, are you cheating over there? How do you know arctangent of 0 is 0? You put it, okay, so you put it in your calculator. All right, you were ahead of me there. All right. So that's okay, but you might run into a problem on the next step. So let's think about this. Do you remember class 2412 pre-cal? Okay, that is the graph right here of tangent of x. That's not the graph of arctangent. That's the graph of tangent. So when you say, what is arctangent of 0, what you're really saying is on the tangent function, where is your y-coordinate 0? So at what x-coordinate is your y-coordinate 0? At 0. Okay? Now that's going to be useful in the next step. So this right here is 0, isn't it? And this one over here is 0. Wonderful. Limit time. I'm trying to figure out what arctangent of t is. And I'm about to let t go to negative infinity. So on your calculator, what's arctangent of negative infinity?
I don't know. It just gets bigger, right?
Yeah, so the calculator is going to have a problem with negative infinity as an input, right? Yeah. So what we need to do is understand what's happening on the picture. When we say arctangent of infinity, that's really what we're about to do here. We're about to say arctangent of infinity, negative infinity. What we're really saying to ourselves is that what x-coordinate is our y-coordinate negative infinity. So it never really gets to negative infinity, does it? I mean, like the graph does this. It starts heading to negative infinity, right? But it never gets there. But the closer our x-coordinate gets to what? What is this point right here? Where do we have that vertical asymptote? Negative pi over 2. That's the vertical asymptote of the tangent function. And this one right here is pi over 2. So that, again, pre-cal. So as our x-coordinate moves to negative pi over 2, the tangent function dives down to negative infinity. So the inverse tangent of negative infinity is negative pi over 2. That. Yes or no?
Oh, yeah.
Okay, so this is going to be minus negative pi over 2. And then we have here plus. Now, what is arctangent of r if r is going to infinity? So this is saying what's arctangent of infinity? This time it's pi over 2. So the tangent function heads to infinity as you head to pi over 2. So this is pi over 2, and then minus this 0 over here. So we've taken the limits now. So we get 0 plus pi over 2 plus pi over 2 minus 0, which is pi. This converges to pi. Did somebody in here ask the other day what pi was? Someone asked what pi was? Did you ask what pi was? And we were talking about circumference over diameter. If you wanted to, if you were so inclined, you could define pi to be the area underneath that curve. Because it's pi, right? Yeah. So you could define pi as the area below this function on the entire number line. That would be a perfectly valid definition for pi. But you could just as easily come up with about a billion other definitions for pi. Why do they call it pi? So they use Greek letters. Okay, so pi is a lowercase p, right? So mathematicians like to use Greek letters to represent important numbers. Now there might be an actual reason why they used the Greek letter pi, like why they used that letter. But they could have used sigma. They could have used gamma. They could have used epsilon. They could have used any Greek letter.
That symbol, that's the symbol like pi?
That symbol pi is just a Greek letter.
Okay, so that's the Greek letter.
That's a Greek letter.
Okay.
Yep.
Like other languages, do they use like tangents?
Other
Chinese?
languages?
Yeah, like Chinese, do they use
We all have the same functions. I'm not quite sure whether or not they would call it tangent or use the same notation. I'm pretty sure it's not the same exact. They don't write TAN because they're not using English letters. So they would have their own notation for it, but the function itself is the same.
So the Greek letter pi, you said it's a lowercase p?
Yes.
So why don't they just use that instead of that?
But that is the lowercase Greek letter. So you have, the Greeks had their own alphabet, all right? And so they had like S and T and R, but they had their own symbols for it. Just go Google the Greek alphabet, and you'll see that for every letter we have, there's a Greek letter that corresponds to it. Yeah, so they just picked pi. I don't know. Maybe there's a historical reason behind it, but...
From doing math, do you know the whole Greek alphabet?
I don't know the whole Greek alphabet. I don't... Because you have lowercase and uppercase. Let me see here. Typesetting. Here we go. See, there we go. There we go. So can you see these? Whoa, sorry, I need to erase my stuff. We're done with this problem, right? The answer was pi?
Oh, that one's that weird trident one.
Yeah, so these are the Greek letters here. So we've got that's pi, capital pi. That right there, capital rho.
Yo, is that theta?
Sigma, there's sigma, we use that, right? Tau. Epsilon. This is lowercase epsilon. Delta. Gamma. Beta. Alpha. What do we use in pre-cal? theta, right? We're just using Greek letters in math. Just because. Now, what I've always found weird is, we use e to the x, right? E to the x, the exponential, and we use e. We don't use a Greek letter for e, but e is just a number like pi is. So I don't know. There's probably historical reasons, but
Euler?
Euler's number, probably from Euler. Yeah, the e is from Euler. But we could have called it epsilon. That's what I'm saying. We could have used epsilon instead of the letter E, because the Greek alphabet. But okay, hey, look at this one. Okay, so that's the one I asked you to do, right? All right, so I'm going to move kind of quick through this one because you've already done the integration, right? Okay, so look at this one. I'm kind of running out of time here. This is going to go from negative infinity. Let's go to 0 again, of x e to the x dx. And then we're going to go from 0 to infinity of x e to the x dx. So that's just me splitting it up into two. I choose to go to 0 and then continue from 0. This will be the limit. I'll use t goes to negative infinity of, can I go ahead and take the antiderivative now? Is that okay? Yes? Let me just take the antiderivative, which we said was x e to the x minus x, right? And then we're going from t to 0. Plus limit r goes to infinity, and then x e to the x minus e to the x, and then 0 to r. So that's pretty much the same setup as last time, right? Now, we get to plug in, right? So limit t goes to negative infinity. I'm going to have two things here, plus limit r goes to infinity. I'm going to have two things here. So we plug in 0, right? Am I moving too fast on this, or is this okay?
No.
Okay, let's plug 0 into this. We get 0 times e to the 0 minus e to the 0. Then we're going to plug t into this. So t e to the t minus e to the t. And then we get to plug r into this one. So r e to the r minus e to the r. And then 0 into this one, 0 e to the 0 minus e to the 0. Let's take care of the things we know we can take care of right now, which are the e to the zeros, right? So what does this become right here? Negative 1. That's gone, right? And then you have e to the 0, which is 1, so we get negative 1 here. And then this one back here, negative 1 again. Okay, I'll put it in parentheses because we're going to have a negative in front of it. All right. What next?
Plug in the infinity for t.
Yeah. Here we go. Okay, this is where things start to get a little messy. I've got to let t go to negative infinity right here, right? That's what I've got to do? That looks a little bit messy. So here's what I'm going to do. I'm going to do some scratch work on the side here. I'll do it right here. I'm back in Cal 1 now. I'm taking the limit as t goes to negative infinity of t e to the t minus e to the t. That's what I'm about to do. So let's talk about what happens. Yeah, we get some crazy stuff happening here. T is going to negative infinity, right? So this goes to negative infinity, right? times, now be very careful here. What does e to the t do as t goes to negative infinity? It basically makes it 1 over e to the infinity. So there's kind of two ways you can look at this. If I were to ask you to graph e to the t, this would be e to the t, right? That's your basic exponential function. But if you're letting t go to negative infinity, you're saying what happens to this function as we go to negative infinity? It goes to 0, which is the same as looking at it as 1 over e to the positive infinity, either way. But that goes to 0. Okay, minus, now what does this one go to? Well, that's the same as that one, right? So that goes to 0. Right?
Oh, wait. Negative infinity times 0.
So the problem here is not this. This is okay.
Yeah.
The problem is this. This right here is an indeterminate form. Okay? So, yeah, how do you handle that? Now, you can redeem yourself by telling me how to do this limit. I don't mind if anyone's here on their phone doing whatever, but if you can't do this, that's not what you should be doing. You should be asking questions, paying attention, figuring out what you need to do to make this make sense. So do you know how to do a limit from Cal 1 when you have infinity times 0?
0, because if it's negative infinity times 0, what? 0.
Okay, so earlier, right? Earlier, didn't I say this was an indeterminate form?
Yeah.
Okay, this is not 0. I said that specifically earlier today, that this is not 0. So it's indeterminate form. So does anybody remember how you attack something like that? Yes?
Once you take the derivative, you use L'Hopital's rule.
You can use L'Hopital's rule, but remember L'Hopital's rule only works when you have infinity over infinity or 0 over 0.
Oh, you're right. You're right.
You have to have that.
Yeah.
You have to turn it into one of those. So how do you turn that into one of those?
Over what you inverse, you put it over reciprocal.
You pick one of these,
Yeah.
whichever one you want, and you drop it to the denominator. Now that sounds like, how do you do that? Like, that's crazy. All right, so what we do is we take limit, t goes to negative infinity, and I get to choose which one of these I want to drop. So what I'm going to choose to do is leave the, I don't know, okay. I'll leave the e to the t on top, okay? No, I'll do it the other way. I'll leave the t on top, and I'll drop the e to the t on the bottom, but when I do that, doesn't it become negative t? Like algebraically, I can't just move something down. I can rewrite it. This is this, right?
Yeah.
And notice I'm ignoring this because I don't care. That goes to 0. All right? So this right here, now I ask myself what happens when you take the limit. So this time in the limit, negative infinity, right? T goes negative infinity. Top goes to negative infinity, right? Now what does the bottom do? That's negative t now, right? And we're plugging in negative infinity. So this is saying e to the positive infinity. And back at your picture, e to the positive infinity goes to infinity. So now the bottom goes to infinity. Now the fact that it's negative over positive doesn't matter. For L'Hopital, all you need is, this can be plus or minus, this can be plus or minus, doesn't matter. As long as you've got the ratio of an infinite expression over an infinite expression, you can use L'Hopital's rule. Which is, what does L'Hopital's rule tell you you do now? Take derivative of the top and bottom separately and evaluate that limit. So I'm out of space over there. So I'm going to say that that's equal to, and at least in my classes, I always tell my students to put an L with a circle around it to let everyone know they're using L'Hopital's rule. But in books, you use H. A lot of the books use H here. I use L'Hopital because L'Hopital, right? But okay, so limit t goes to negative infinity of derivative of that, 1 over derivative of this, negative e to the negative t. You have a little bit of chain rule there, right? Derivative of e to the t is itself, negative t is itself, but then times derivative of what's up top, negative 1. And now take this limit again. So let t go to negative infinity. The top this time is 1, right? The bottom, that right there goes to what?
Negative infinity, right?
That goes to infinity, and then that's negative. So negative infinity, and that goes to 0. Okay, so this goes to 0, and that one went to 0, so that means this whole thing goes to 0. You have to show that on a test. You can't just say, oh, that goes to 0 without any proof of that, okay? All right, you okay with that? We're not done. We got to do this one. And this is not exactly the same because it's the same expression, right? But r is going to positive infinity, not negative infinity. Right? So let's see what happens here. I'm going to do that as its own problem up here too. I warned you that L'Hopital was coming. Okay, I'm taking the limit as r goes to positive infinity of r e to the r minus e to the r. And let's crank this thing out, see what happens. R is going to infinity, that's this, times infinity again, right? Because we're going to positive infinity, so that's infinity. Now infinity times infinity is infinity, all right? So that's good. But then minus what? Infinity, crap. So we've got infinity minus infinity. Infinity minus infinity is not 0. That is an indeterminate form. Look, you got something that's getting really big, right? Minus something that's getting really big. That doesn't mean 0, it means you don't know. It means you have to figure out how fast this one's getting big, how fast that one's getting big. So anyone remember what we try to do when you have infinity minus infinity? Factor. Good. Good. Are you cheating too? You use your calculator? So you just remember that? Good. So you factor. You try to factor. E to the r. E to the r. Right? And then r minus 1. Now, the whole point of factoring is that you're hoping that this can be something that you can deal with now. So let's try it again. Run the limit. E to the r goes to infinity. Doesn't that go to infinity? Times, now that's infinity minus 1, right? Infinity minus 1 is still infinity, right? Like it's becoming infinite. And now you've turned infinity minus infinity into infinity times infinity, which is infinite. And that means that this is infinite, and this one was 0, wasn't it? And it all doesn't matter. Everything we've done now doesn't matter because this one goes to infinity.
Oh, wait, no, that's minus.
Oh, this one was 1, sorry, right? It was 1? Minus negative 1? Yeah, thank you. That was, so we've got infinity plus 1, still infinity, and then over here you had like minus 1 or something, who cares? It's infinite. What's the answer to this then? It diverges. Okay. Yes?
So on a test, I'll just put divergence.
Yes, after you do all the work?
Yeah.
Yes. Yeah, I mean, you could flip a coin, go for it, but yeah, you won't get any credit. Yes, so do this, right? I mean, these become difficult for me to grade, because, not difficult, but I'm looking for all this work, right? I'm looking for you to show that when you got to this, you understood that you had an indeterminate form and then took it and got a result. And then at the end, yeah, it diverges.
So would you, for the answer, would you have to put up, like, infinity, square that, and then put divergence next to it?
I would put infinity, maybe box it and put diverges next to it.
Yeah.
Yeah. But again, it's going to come down to your work. I'm going to be looking at your work more than I'm going to be looking at anything else. Okay, so let's see what else we got here.
On ones that converge, is it stated like converges
Or two of.
at 2?
I think it says like evaluate the integrals. If it converges, state what it converges to. Otherwise, say it diverges. All right, this is the last little thing here. This is a function. This is just more of an FYI. I know I have like 2 or 3 minutes. This is an exponential function. Now, here's our basic exponential function, e to the x, right? But I could put a number out in front of this, like maybe like 1/2, and that would change its shape. And then I could put maybe like 3x, I don't know, over 4, and that would change its shape. Well, if you do all of this to a function, you take 1 over the square root of 2 times Greek letter, sigma times pi, e to the, and then you take x minus mu squared, make that negative, divide by 2 sigma squared. If you graph this function, you get what we call our standard normal distribution, which you have probably heard as being the bell curve, right? Oh, why is that so big? Your bell curve. So mu, in that formula up here, the mu, which is that one right there, the mu is the average, the mean of the population or the data. So you can change your mean, and then you can change your standard deviation, and it changes the shape of your bell curve. Here's what's important about this. This is why I'm bringing this up. Let's talk about how tall human beings are. Okay, human beings. If you were to take the average human being, right, and see how tall they are, I think it would be safe to say that their height would be more than anything negative, right? In fact, we couldn't have negative. So you would probably need to adjust this, like to make it look more like this. So this is looking like, if I just take this graph, let's say from here in just this part right here, and then go this way forever, then most people are going to lie somewhere 5 foot or so. Does that kind of make sense? And I mean, 10 foot? No, right? But this is what we call a probability density function. And what it represents is the probability of somebody being a certain height. So about 5 or 6 feet tall, you have a very high probability. But outside of that, your probabilities start to drop down. Now, what's the probability of someone being 15 feet tall? Zero or low? Low, very low, right? Very, very, very low. But you can't say 0. So what happens is you get this function, right? And over here you got very small numbers. So the area underneath this, the total area, and this is the kind of the big kicker of it all, the total area under that curve has to be 1 because it is the sum of all of the probabilities. Think about it this way. If you had a 6-sided die and I rolled it, there's 1 of 6 outcomes, right? Each outcome has an equal probability, 1/6, right? The sum of all probabilities has to be 1. That's a fundamental principle of probability, right? The probability of the sum of all the events must equal 1, which means that the sum or the area underneath this entire curve would have to be 1. And in fact, if you were to take that function right there and integrate it, which I had my computer do it for us, if you integrate it, you get 1.
So you cheat.
Yeah, I cheated. Well, I didn't cheat completely because this function right here, we cannot integrate with any technique we have. You have to use power series, and then we haven't talked about that yet. But the standard normal distribution in all probability density functions, oops, how did that happen? All probability density functions have to have a total area of 1 under them. For your homework, for this section, since I know you want to get started, look at problems 1 through 31 odd. Only do the problems that have infinities in the limits of integration. If the problem does not have an infinity here or here, skip it. That's type 2, and we're going to do that next class. All right? Okay. I guess that's it for the... I'll try and send something out on Friday for the class for some sort of guide.